What if reality isn't chaotic, but calculated? Imagine standing at the edge of a river. You scoop up a handful of pebbles, toss them back, and watch the water ripple outward in unpredictable patterns. Chaos, it seems, pure, unstructured, random. But what if that impression is an illusion? What if the very fabric of reality, even in its most chaotic forms, is built on hidden mathematical structures? That's the haunting proposition at the heart of a quiet revolution, one that's not being shouted in headlines, but whispered across disciplines, from quantum physics to economic theory, from geology to fluid dynamics. Researchers keep finding the same thing: patterns, exact ones, universal ones, patterns that should not exist if the universe were truly random. Frank Benford, a physicist in 1938, noticed that numbers in nature didn't behave the way we'd expect. When measuring lengths of rivers, or tracking populations, or analyzing stock prices, the first digit was more often a 1 than a 9. Not by a little, but with a predictable mathematical precision. This became known as Benford's law. It didn't just show up in accounting data, it emerged in earthquakes, molecular weights, even the Fibonacci sequence. Everywhere, but that was just the beginning. Look closer at turbulence, the swirling madness of storm clouds or boiling water. Chaos incarnate. Yet the energy across different scales of turbulence obeys a strict mathematical law. The same law, regardless of whether the fluid is air, water, or plasma, drifting through galaxies. Zoom in again to the microscopic quantum world. Electrons, unmeasured, exist in superposition, multiple states at once, but when observed, they collapse into a single state. This collapse appears random, yet statistically, the outcomes match quantum predictions with uncanny precision, not approximately perfectly. Every time, even deeper, you find the fine structure constant. An odd little number, approximately 1137, that governs how particles interact with light. It's a pure number, dimensionless, unit-free, essential to how atoms form, how chemistry works. But we don't know why it has this value. It just is. If it were different by even a sliver, life as we know it wouldn't exist. These are not isolated mysteries. They form a constellation of clues, a set of fingerprints left behind not by chance, but by design. Not necessarily a divine one, but perhaps a computational one. Suppose the universe is not a vast mechanical clock, but a program, a simulation. In this view, the patterns we detect aren't just mathematical quirks. They're the outputs of underlying algorithms. Benford's law, the strange attractors of chaos, the perfect randomness of quantum mechanics all behave like compressed code. Efficient, recursive, optimized. In the same way a computer game doesn't calculate every leaf on every tree in advance, reality may render complexity only when required, on demand, in response to observation. This is the story we're about to explore. Over the next 13 chapters, we'll walk the narrow line between order and disorder, examining 10 patterns that appear in places they shouldn't, from black holes to cellular automata. Each step reveals something deeper, that what looks like noise may in fact be signal, and that even chaos might be an echo of code. This isn't about proving simulation theory. It's about contemplating its possibility and what that would mean for our understanding of reality, memory, and meaning itself. Because if even chaos is programmed, then what is freedom? What is randomness? What ultimately is real? And if we are part of a grand computation, who or what is running it? Let's begin. It started with a number that refused to behave. In the late 1930s, Frank Benford, a physicist with a curious mind, stumbled upon something strange. While flipping through pages of logarithmic tables, those dusty tools of pre-digital math, he noticed that the earlier pages, the ones dealing with numbers beginning with 1, were more worn than the rest. More than curiosity, it felt like a glitch, a fingerprint of something he couldn't name. He decided to test a hypothesis. Maybe numbers in the real world preferred to begin with certain digits. So he gathered data, lots of it, the lengths of rivers, atomic weights, street addresses, stock prices, death rates. The results were consistent, eerie. The digit 1 showed up as the first number nearly 30% of the time. The digit 9, less than 5%. This wasn't noise, it was a law that shouldn't exist. Today we call it Benford's law, and it defies what we expect from randomness. Think about it. Why should the length of the Mississippi River begin with a 1 more often than a 2 or a 3? Why should earthquake magnitudes, tax returns, and the half-lives of isotopes follow the same pattern? Different causes, different domains, yet the same mathematical rhythm pulses through them all. The explanation on the surface sounds mathematical, something about logarithmic scales, multiplicative growth, and base invariance. But none of that explains why reality prefers these scales to begin with. Why is so much of nature inherently logarithmic? Why is the pattern so persistent, so universal? It gets stranger. The law holds in datasets you'd expect to be random, or at least unrelated. The Fibonacci sequence, the powers of 2, the sequence of prime numbers. Even fabricated data fails to mimic Benford's distribution. In fact, forensic accountants use it to detect fraud. Humans trying to fake randomness often distribute digits evenly, betraying their efforts. But reality? Reality is not even. It's efficient. If you were designing a simulation and you wanted to save computational power, you might compress data by prioritizing lower digits. You'd use logarithmic scaling, repeating structures across different magnitudes. The world would appear complex, but under the hood, the same rules would play out again and again, like fractals in number form. And maybe that's what Benford's law is, the faint signature of an algorithm, a recursive rule used to govern a digital universe pretending to be analog. When researchers push this further, the implications turn uncanny. They find the law in the metadata of computer files, in the addresses of streets, even in how news articles use numbers. From the smallest particles to the largest economies, the pattern persists. It's as if the universe is quietly counting in a language of its own, a language hidden in the shadows of our assumptions. So we're left with a strange realization. Benford's law isn't just about digits. It's about design. It hints at a deeper order masquerading as randomness, a rhythm threading through every scale of existence, a whisper from the code that runs beneath. If a single numerical pattern can emerge in physics, biology, economics, and human behavior, then maybe these aren't separate systems at all. Maybe they're modules in the same machine, variations on a theme, subroutines called by a larger program. The digits aren't lying. They're telling us that reality counts, but not the way we thought. A solar system, a pendulum, a pair of dancers in space. For centuries, physicists believed the universe was like a grand clock, deterministic, mechanical, precise. Newton's equations could predict the path of a falling apple or the orbit of the moon. Cause led to effect. Order reigned. But then came a question that broke the mold. What happens when you add just one more body. The three-body problem. Take three objects, say three stars, and try to predict their motions as they pull on each other with gravity. It sounds simple, but it's not. The equations explode into chaos. Tiny changes in starting positions lead to wildly different outcomes. The system becomes exquisitely sensitive, fundamentally unpredictable over time. This isn't just a curiosity, it's the essence of chaos. But chaos, it turns out, hides something unexpected. When mathematicians mapped the trajectories of three-body systems in phase space, a kind of multi-dimensional map of all possible states, they discovered strange attractors. These are not simple loops or spirals. They are complex, fractal-like structures that chaotic systems tend to follow. The paths never repeat, yet they're not random either. They hover, curve, twist, but always stay near these invisible forms. It's as if the chaos is being drawn toward a shape carved into the fabric of reality. The most famous is the Lorentz attractor, which came not from celestial mechanics, but from weather modeling. It looks like a butterfly, endlessly flapping its wings through three-dimensional space, never quite landing, never quite repeating. And here's the marvel. These attractors appear in wildly different systems, not just stars or storms, but chemical reactions, heartbeats, electrical circuits, different laws, same kind of pattern. How is that possible? Some researchers suggest that strange attractors are the signatures of compression. If a chaotic system needs to be rendered efficiently, say, in a simulation, you wouldn't calculate every possible outcome. You'd use a rule, a shape, a boundary. The system would seem free, but it would be bound invisibly by a structure. This is how computer simulations of chaos work. Instead of running every particle, you define an attractor, a compact mathematical form that governs behavior. What looks random is actually constrained by code. What if the same is true for our universe? What if the chaos in weather or the complex dynamics of a planetary system is following not natural randomness, but compressed algorithms, subtle rules that generate complexity from simplicity? Strange attractors may be more than just mathematical curiosities. They might be windows. Through them, we glimpse the hidden architecture beneath disorder. In a purely physical universe, governed only by matter and chance, we would expect chaos to be just that: chaotic, spread out, unpredictable. But in our universe, chaos gravitates toward form, toward geometry, toward something that looks like intention. Why should that be? Why should stars dancing in gravitational madness draw invisible butterflies in phase space? Unless the universe is not just calculating behavior, but optimizing it, not just running, but rendering. And so the three-body problem, once thought unsolvable, becomes something else entirely, a message from the deep logic of reality, whispering through patterns we can't ignore. Even chaos, it seems, knows where to go. What if randomness could be perfect? In the subatomic world, particles don't behave the way we expect. They shimmer in a cloud of probabilities, existing in many possible states at once, until we observe them. Then the cloud collapses. The particle chooses a state, up or down, here or there. It's called quantum superposition, and its collapse appears random. But not just any kind of random, a very specific, strangely obedient kind. Take the spin of an electron. Measure it 1,000,000 times under the same conditions, and the outcomes follow the predicted probabilities exactly, down to the decimal. Not approximately, not roughly, but precisely. This is not how randomness usually works. True randomness, the kind we imagine when we flip coins or shuffle cards, doesn't care about matching predictions. It fluctuates, it varies, it wanders. But quantum randomness is unnaturally consistent. It follows rules so tightly, it's as if the chaos itself is scripted. It gets weirder. Quantum tunneling allows particles to slip through barriers they shouldn't be able to pass. On a single trial, it's unpredictable. But over many trials, the rate of tunneling matches calculated probabilities with uncanny precision. And then there's quantum entanglement, when two particles become linked so that measuring one instantly determines the state of the other, no matter how far apart they are. Each result seems random, but the correlation between them? Perfect. Always. This kind of randomness behaves more like a computer's pseudo-random number generator than anything truly spontaneous. A generator doesn't produce numbers out of nowhere. It uses an algorithm, a seed, and deterministic math to output numbers that only appear random. Underneath, it's all code. Some physicists have begun to see quantum behavior not as particles interacting physically, but as information being processed. The wave function? Not a physical wave, but a distribution of possible information states. Measurement? An act of extracting that information. In this view, particles are data points. The universe is an information processor, and quantum randomness is not uncaused mystery, but output, rendered on demand. One of the strangest pieces of evidence comes from the delayed choice quantum eraser experiment. In it, photons behave differently based on measurements made after they've already been detected. It's as if the past is rewritten to match present knowledge, as if the universe recalculates the story to ensure it all makes sense. This isn't just bizarre, it's computationally elegant. In programming, we often design systems to resolve all constraints consistently. A simulation might calculate forward and backward at once to create a coherent result. If a late decision changes earlier requirements, the whole timeline is adjusted. What if our universe works the same way? Then quantum collapse isn't random at all. It's a calculation, a rendering. The outcome looks spontaneous, but it's the result of hidden logic obeying deep mathematical principles. This would explain why quantum measurements never contradict the math, why the randomness is perfectly ordered, why particles wait to collapse until someone checks. Because in a programmed reality, nothing is real until it's needed, and nothing is wasted. So the next time you hear about quantum uncertainty, remember, it might not be the mark of chaos. It might be the signature of a system designed to appear uncertain, while following rules more precise than we can comprehend. An illusion of randomness hiding a deeper code. Reality doesn't just calculate, it curates a blank grid. Just black and white squares, lifeless, still. Then, the rules begin. In 1970, mathematician John Conway created something deceptively simple, a cellular automaton he called the game of life. On a two-dimensional grid, each cell could be alive or dead. 3 rules governed their fate. Live cells survive with 2 or 3 neighbors. Dead cells come to life if they have exactly 3, and everything else fades away. That was it. No intelligence, no programming of patterns, just rules applied again and again. What emerged shocked everyone. From random beginnings, order bloomed. Structures formed, some danced across the screen, gliders, others spat out gliders endlessly, glider guns. Entire systems of self-replicating, computing machines arose out of nowhere. The game of life could simulate logic gates, memory, even other automata. It was proven Turing complete, able to compute anything a real computer could, and all of it came from 3 lines of code. This is the revelation of cellular automata. Complexity doesn't need complexity, to begin. It only needs iteration. Stephen Wolfram spent decades exploring this idea. He catalogued thousands of rule sets, discovering that many of the simplest ones produced behavior that looked random, chaotic, beautiful. Rule 110, just two colors and a few neighboring cells, was enough to simulate universal computation. It was the minimal spark needed for digital fire. And these automata didn't just look like they were simulating things, they looked like the world. Fractal-like structures, patterns that resembled tree branches, river systems, even DNA replication. If the rules were tuned just right, at the edge between order and chaos, something extraordinary happened. The system came alive, not in a conscious sense, but in the sense that it did things. It computed, it self-organized, it created phenomena that looked planned but weren't. That's the same space our universe seems to inhabit. We live in a cosmos that is neither fully ordered nor truly chaotic. Galaxies form patterns. Life evolves structure. Snowflakes crystallize into intricate symmetry. And yet randomness is always near, waiting in weather systems, gene mutations, and the roll of quantum dice. This edge of chaos, the narrow window where complexity thrives, is where cellular automata find their magic. It's also where our universe operates. Shift the physical constants just slightly, and stars don't form, or atoms collapse, or everything freezes in place. But here, in this fragile middle zone, complexity blooms. If you were building a simulation, this is exactly how you design it. Simple rules, efficient computation. No need to hard-code complexity. Let it emerge. Set the parameters so that rich, unpredictable behaviors form naturally, saving enormous resources. Let the rules do the work. Let the system build itself. And that's what makes cellular automata feel less like models and more like blueprints. They show that a universe like ours doesn't need to be written line by line. It only needs rules. The kind of rules that can fit on the back of an envelope, but play out across billions of light years and billions of years. A glider moves across a grid. It doesn't know it's simulating motion, but it is. Maybe we're not so different. Maybe we're the gliders. The outcomes of rules so simple, we've mistaken them for randomness. Not because we lack imagination, but because the code was never meant to be noticed, only lived. It's just a number. 1 divided by 137, a decimal without units, a whisper from the deep architecture of reality. Physicists call it the fine structure constant, denoted by the Greek letter alpha, I. It governs how charged particles interact with light, how atoms form, how chemistry unfolds, and how the universe holds itself together. It is everywhere, yet nowhere explained. Roughly 137.35999, a number measured to more than a dozen decimal places, with theoretical predictions that match observations exactly. It's not a ratio of units. It's a pure number, dimensionless, untouched by our systems of measure. And yet, change it by even a small amount, and the consequences are catastrophic. If alpha were slightly larger, electrons would spiral into nuclei. If it were smaller, atoms would fall apart. Chemistry wouldn't work. Stars couldn't fuse elements. Life would never form. In short, reality depends on this number being exactly what it is, and yet no one knows why it is. It doesn't derive from other constants. It doesn't emerge from deeper theory. It's just there, etched into the source code of the universe, like a parameter set before the program runs. Richard Feynman called it one of the greatest damn mysteries of physics, a number that has been a mystery ever since it was discovered, a magic number that comes to us with no understanding by man. We've searched for meaning in its digits. We've speculated about cosmic numerology, but no pattern reveals itself. It's like a password without a hint, a lock without a key. And yet, it behaves as if chosen, because if you were designing a simulation, you'd need constants like these. You'd define values that control how forces interact. You'd tweak those values so that complexity could emerge, so that your simulated world could evolve stars, elements, and life. The fine structure constant feels like one of those values. Not derived, not emergent, chosen. It also stays the same. Everywhere, always. Light from galaxies billions of light years away shows the same alpha. It hasn't drifted or degraded. Across time and space, this number remains fixed, stable, like a setting in a system that never loses track of its configuration. It gets more mysterious. Some researchers have found elegant, if speculative, relationships between alpha and other physical constants. Connections too clean to be coincidence, yet still unproven, like lines of code referring to one another behind the scenes. The outlines of a deeper architecture we haven't yet deciphered. And then there's the precision. Reality doesn't usually offer such exactness. Physical systems are messy. Yet alpha is measured and calculated with astonishing agreement, as if it's not a property of matter at all, but of math. This is what you'd expect if the universe is executing a program, because a program doesn't deal in fuzzy approximations. It runs on precise values, exact parameters, rules that don't drift because they can't. So here we are, orbiting a number we cannot escape, a constant we rely on but cannot explain, a cornerstone of physics that might be nothing more than a line in the configuration file of the cosmos. What is alpha? A coincidence, a consequence, or a clue? Because if it is a clue, then it's telling us something we've long suspected but rarely dared to say, that the universe isn't just made of particles and waves. It's made of information, set to parameters, running on code. A coastline stretches across a map like a torn edge, jagged, irregular, impossible to measure with certainty. It's one of the simplest questions you can ask. How long is a coastline? But the answer depends on how closely you look. Measure it with a yardstick, and you get one length. Use a foot-long ruler, and the length increases. Zoom in further, inch, centimeter, millimeter, and the coastline grows longer still, endlessly more complex. This is the paradox of fractals. In the 20th century, mathematician Benoit Mandelbrot gave it a name: fractal dimension. Unlike ordinary shapes, which have whole number dimensions, lines are 1D, squares are 2D, fractals exist in the space between. A coastline might have a dimension of 1.25, more than a line, less than a surface. Mountains, about 2.2. Clouds, around 2.4. And these values stay consistent across vastly different examples. Different rivers, different cloud systems, different mountain ranges, same fractal dimensions. That shouldn't happen. These are chaotic systems, driven by different physics, geology, fluid dynamics, erosion, evaporation. They should produce different patterns, but they don't. The complexity always hovers within a narrow mathematical range. Why? Fractals aren't just chaotic, they're efficient. Tree branches follow fractal rules to maximize sunlight exposure. Blood vessels and bronchial tubes branch in fractals to distribute nutrients and oxygen efficiently. River networks carve landscapes into recursive patterns that optimize flow. Even fungi, lightning bolts, and coral reefs follow the same recursive logic. These systems weren't designed by a conscious architect. They emerged, but not randomly. Fractals are nature's compression algorithm. They allow infinite detail without infinite information. With a single recursive rule, a system can generate complexity that fills space in just the right way. It's what computer graphics do: generate trees, coastlines, and landscapes using fractal formulas. You don't store every detail. You run the rule again and again, and the result looks natural, because it is. Or maybe because nature is computational. The same fractal dimension that describes clouds in the sky also describes the digital clouds in your video games. The same recursive patterns that carve out coastlines also shape the data structures in procedural generation. If the universe is a simulation, this is exactly what you'd expect. Instead of wasting resources rendering every molecule of a mountain, the system uses recursive algorithms. Instead of drawing every leaf, it generates patterns from simple rules. Efficient, scalable, seamless. The consistency of fractal dimensions across systems suggests something profound, that what we call natural chaos is actually a tightly optimized routine, that rivers and trees and lightning bolts are not just physical phenomena, they're outputs of code. This doesn't diminish their beauty, it enhances it. Because if a tree is a program, it is also a poem, written in recursive logic, blooming from simplicity into infinite complexity. And the coastline? It may not have a single length, but it has a fingerprint, a fractal dimension, one that matches other coastlines on other continents, drawn by different forces but shaped by the same invisible pen. Because maybe it's not the forces that matter, maybe it's the function. Picture a storm. Water churns, air twists, leaves scatter, chaos reigns, and yet beneath the surface something precise is happening, something mathematical, something universal. Turbulence, the epitome of unpredictability, follows rules, not loosely, not sometimes, but with a consistency that defies its wild appearance. It starts with energy. In a turbulent flow, whether wind, water, or plasma, large swirls break into smaller ones. Those break again, cascading down to ever tinier scales until the energy dissipates as heat. This cascade follows a law, the Kolmogorov spectrum. The energy at a given scale drops according to the size of the swirl, following a power law, specifically L to the -5/3. That ratio appears everywhere, in ocean currents, in cloud formation, in the solar wind, in galaxies. Different materials, different conditions, same curve. Why? Because turbulence, it turns out, is not truly chaotic. It's structured randomness. It's what happens when systems with too much energy try to self-organize. We see it in weather, in blood flow, in rocket engines, even in interstellar gas clouds. And always, the same power law distribution, the same whisper of mathematics guiding the dance. Dig deeper, and the patterns continue. Richardson's law shows how particles in turbulent flows drift apart over time. Not randomly, but in a predictable way. The distance grows with time to the power of 3/2. Again, a precise curve. Again, a universal exponent. Then there's intermittency, those sudden bursts of turbulence in the middle of calm. You might expect these to be purely random, but no, they follow multifractal distributions. Patterns within patterns. Predictable unpredictability. Even stranger, inside the storm, coherent structures arise, swirling vortices that persist like ghosts. They form, drift, merge, and vanish, but not aimlessly. They obey deep geometry. In phase space, their paths often trace strange attractors, just like the three-body problem or Lorenz's butterfly. It's as if the chaos is running on rails. Why would that be? In the language of simulation, turbulence looks like a subroutine, a general-purpose algorithm, reusable across contexts. You wouldn't program turbulence differently for wind, water, and plasma. You'd write it once, an efficient routine that generates rich behavior wherever it's needed. And that's what the universe seems to do. Different systems, same output. Not because of shared materials or forces, but because of shared math. This is what you'd expect in a computational universe. A function call generate turbulence input that produces chaos which isn't truly chaotic, just deeply compressed. And if that's true, then what we see as disorder is really design. Not conscious, perhaps, but intentional. Not engineered, but executed. It means the storm is not just a metaphor for chaos. It is a message, a beautifully disguised one. Because the next time you watch water boiling in a pot, or feel wind gusting past your face, know this: you are witnessing a pattern older than time, a universal behavior written in the language of power laws and fractal cascades, not random, rendered. Because even the storm follows code. A single grain of sand falls onto a pile. Nothing happens. Another lands. Still nothing. But then one more grain and the pile shifts. A tiny avalanche, a cascade, then silence again. This is not just a metaphor, it's a model. In 1987, physicist Purbach studied sand piles and uncovered something extraordinary. As grains are added, the system self-organizes to a critical state. It doesn't need outside tuning. It finds the edge of instability on its own. And once there, avalanches occur. Small ones are common. Medium ones, less so. Large ones? Rare, but not unpredictable. Their sizes follow a power law distribution. A precise mathematical curve describes the chaos. This phenomenon was called self-organized criticality. And it didn't stop with sand. Earthquakes follow the same pattern. So do forest fires, stock market crashes, solar flares, even neural avalanches in the human brain. Entirely different systems: geological, biological, economic, astrophysical, all producing events that scale the same way. What do tectonic plates and trading floors have in common? Nothing physical, but everything mathematical. These are complex systems with many interacting parts. They accumulate tension or energy gradually, then release it suddenly, unpredictably in the small, but perfectly predictable in the large, a kind of structured instability. And it hints at something bigger. In a traditional physical model, you need fine-tuned parameters to achieve this kind of balance. But self-organized criticality doesn't require tweaking. The system finds its own balance. It gravitates to the edge between order and chaos, exactly where complexity thrives. This is the same edge of chaos seen in cellular automata, the same critical point where universes are built, not too ordered, not too random. A razor's edge where computation becomes possible, where life can emerge, where intelligence can evolve. It's also what a well-designed simulation might aim for. In programming, you want systems that are robust but flexible, capable of rich dynamics without constant recalibration. Systems that tune themselves. Self-organized criticality is the ultimate design pattern. Set the rules and let the system find its own balance. And that's exactly what the universe seems to do. The recurrence of power laws across unrelated systems isn't a coincidence. It's the signature of shared logic. of a general-purpose function applied across different domains, not coded from scratch each time, but copied, reused, optimized. It also explains why these systems are so difficult to predict in detail. A single avalanche is impossible to foresee, but the pattern, the shape of the probability curve, is always there. Just like a simulation doesn't calculate every grain of sand in advance, it doesn't need to know when the next collapse will occur. It just runs the rule. The outcomes emerge, so when we watch tectonic plates grind, or stock markets crash, or neurons fire in waves, we're not just seeing physical events. We're seeing the expression of an underlying function, a deeper truth, that even in instability, there is order, that chaos can be measured, and that nature, like code, repeats itself quietly, efficiently, universally, one grain at a time. Black holes. The very name conjures darkness, finality, a place where not even light escapes, where space collapses and time twists. For years, they were thought to be cosmic dead ends, matter devoured, information erased. But physics doesn't like erasure. Quantum theory insists that information cannot be destroyed, ever. It can be scrambled, hidden, transformed, but never lost. And that led to one of the most profound paradoxes in science. If black holes consume everything, including the information about what fell in, where does that information go? This is the black hole information paradox. The solution? It may lie not in particles, but in information itself. Over decades, physicists have come to believe that information isn't just a feature of reality, it is reality. Every particle, every force, every field, at its core, is information. The universe isn't just matter in motion, it's bits in operation. And black holes, it turns out, obey the same rules. They have entropy, a measure of information content. And that entropy doesn't scale with the volume inside, as you'd expect. It scales with the surface area of the event horizon. Not the three-dimensional space, but the two-dimensional boundary. That's strange, but it matches the logic of a hologram. A hologram stores three-dimensional information on a two-dimensional surface. And that's what some physicists now believe the universe is doing, projecting our 3D experience from a lower-dimensional information structure. The math backs it up. So does black hole behavior. This is the holographic principle, and it has sweeping implications. It means that space and time might not be fundamental. They might be emergent properties, the result of underlying information relationships. What we call reality could be a rendering, a visual interface for something deeper, something calculated. And black holes are the test case. When Stephen Hawking first showed that black holes emit radiation, now called Hawking radiation, it suggested they might evaporate over time. But if they disappear, what happens to the information they swallowed? Later work proposed that the information isn't lost, but somehow encoded in the radiation itself, like a zip file exploding outward over eons. The paradox, slowly resolving. Even stranger, the amount of information that can exist in any region of space is finite. The Bekenstein bound gives a hard limit based on the surface area and energy of the region. Reality, it seems, has a storage cap, just like a computer. If the universe is simulated, these information limits make perfect sense. A system with finite resources can't track infinite detail. It renders what's needed, stores what it must. Everything else is compressed, approximated, or erased when no longer observed. And maybe space itself isn't a backdrop, but a byproduct, a side effect of information entanglement. In quantum mechanics, entangled particles share information instantly, no matter the distance. It's not that they send signals faster than light, it's that they're already part of the same informational state. Some researchers now believe that space-time emerges from these entangled relationships. Geometry becomes an artifact of information structure, like pixels forming an image. If that's true, then black holes aren't anomalies, they're mirrors. They show us the true substrate of reality, not particles, not forces, but code, rules, bits, boundaries. Information doesn't fall into black holes to die. It becomes part of the equation. And if reality preserves every bit, then maybe, just maybe, we're not as lost as we think, not even in the dark. A photon travels toward a pair of slits. It should behave like a wave, spreading out, interfering with itself, create the familiar pattern of light and shadow on a distant screen. And it does, until you ask which slit it went through. Then the pattern vanishes. Observe the path, and the photon becomes a particle. It picks a side. The interference disappears, as if the universe knows you're watching and rewrites the story accordingly. This is the famous double-slit experiment, but it gets stranger. In the delayed choice quantum eraser, the measurement of the photon's path is made after it has already hit the screen. And yet, whether the interference pattern appears still depends on that later decision. In other words, the photon's behavior in the past is affected by a choice made in the future. This isn't science fiction. It's an actual, repeatable experiment. And it shakes the foundation of causality itself. How can an event be influenced retroactively? The standard answer: it's not that cause and effect are reversed. It's that quantum events don't have definite outcomes until all constraints, past and future, are accounted for. The photon doesn't decide which path it took until the full context is known. This is deeply unsettling if you believe time flows only forward. But it makes perfect sense in computation. In programming, we often solve constraint problems. Given a set of inputs and outputs, we find the values that make the whole system consistent. The solution isn't built step by step. It's derived as a whole, satisfying all conditions simultaneously. What if reality works the same way? What if the universe isn't unfolding like a film reel, but computing like a spreadsheet, updating values forward and backward to keep the equations balanced? Then the delayed choice experiment isn't a paradox. It's a glimpse of how reality calculates. The photon doesn't rewrite its history. It doesn't need to. The history was never fully rendered until all relevant measurements were made. Before that, it existed in a state of informational superposition, not just of position, but of past. Only when the last measurement is made is the full record locked in. This would be an efficient way to run a simulation. Instead of rendering every detail in real time, the system waits. Observations become render calls. Reality is updated only where needed, maintaining coherence with all other known values. It explains why unmeasured quantum states remain indeterminate, why particles don't have definite positions until observed, why entire histories remain blurry until something calls them into focus, because they were never real in the first place, not until the code required it. The delayed choice quantum eraser doesn't prove simulation theory, but it matches it unnervingly well. It shows us that time might be less of a line and more of a loop, that the past isn't set in stone, but computed in context, and that truth, what really happened, might be flexible, not because reality is lying, but because it is calculating. So when we say the universe is strange, we might be understating it, because we're not just living inside a story. We're watching one being rendered, scene by scene, value by value, in a logic deeper than time. Start with a blank slate. Then apply a simple rule. Not 100 lines of code, just one. Something like, if a cell has 3 neighbors, it becomes alive. Now run that rule over and over on a grid. Watch as structure emerges. Shapes appear, move, replicate. Not because someone designed them, but because the rule creates them. This is the power of emergence, and it's not confined to games or simulations. It echoes through the real world. Complexity of galaxies, of weather, of minds can arise from simplicity. But here's where it gets more profound. At the edge between chaos and order, this emergent complexity becomes most vivid. Too much order and nothing changes. Too much randomness and nothing lasts. But right on the boundary, a narrow, delicate threshold, systems become alive with possibility. This threshold has a name, the edge of chaos. In cellular automata, this is where gliders appear, where computation becomes possible. In biology, it's where life arises. In physics, it's where criticality sits, the point where small events can cause cascading effects, like avalanches in a sand pile. And it's where our universe seems to reside. Why does reality operate here? Why do the fundamental constants of nature sit in just the right range for complexity to emerge? Why not a universe of sterile equilibrium or endless, useless noise? Because here, at the edge, is where rich structure forms, where systems can learn, adapt, evolve. If you were programming a universe, this is where you'd tune it. You'd define simple rules that, when iterated, give rise to unexpected outcomes. You'd let structure arise without micromanaging every step. You'd aim for maximum expressive power with minimal code. And that's what we see. From quarks to quasars, the universe behaves like a cellular automaton, scaled up to the infinite. Rules apply locally, yet patterns emerge globally. Galaxies spiral like recursive drawings. Neurons fire like branching networks. Civilizations evolve like evolving codebases. We tend to think of reality as built from the ground up. Atoms forming molecules, molecules forming life. But perhaps it's the other way around. Perhaps what we call particles are just emergent behaviors of a deeper substrate. Perhaps space, time, and matter are outputs, not inputs. In this view, the universe is not a stage, but a system. Not a place, but a process. As a computation running rules at unimaginable scale. And complexity, rather than being designed, is simply allowed, encouraged, set free to unfold at the edge of chaos. It's an elegant solution, one we already use in technology, procedural generation, emergent AI. Simulations that don't hard-code every detail, but instead rely on foundational logic and let the rest arise. If our universe does the same, then what we call nature is not a result of brute force. It's a consequence of clever architecture, and what we call randomness may just be resolution, the unrendered space between the rules waiting to be called into being. Not everything has to be written. Some things can be run, and that might include us. Living patterns, emerging from code. Imagine a library where every book contains not words, but bits. A place where every particle, every interaction, is a sentence written in the language of logic and probability. Now imagine that library has a rule: nothing can ever be deleted. This is the principle of information conservation, a cornerstone of quantum mechanics. And it's more than a rule. It may be the deepest truth about reality. It tells us that even as things change, decay, collapse, vanish, the information they carry is never truly lost. It's preserved, transformed, woven into the fabric of what remains, like ripples that echo long after the stone has sunk. And yet, much of physics was not built to handle this. Classical models often discard information. They allow for irreversible processes, for randomness that erases history. But at the quantum level, reality is more careful, more deliberate. Every action, every collapse of a wave function, follows rules that conserve information perfectly. This points to something startling, that information might be more fundamental than matter itself. The equations of physics describe particles not as solid objects, but as states, configurations of information. Even the vacuum, what we consider empty space, teems with potential. It's not empty. It's a canvas of probabilistic data, ready to collapse into outcomes. Black holes make this even more dramatic. They challenge the idea of information conservation because they seem to swallow it whole. But new theories, supported by string theory and quantum gravity, suggest otherwise. The information isn't lost. It's encoded, hidden on the event horizon, stored like data in a cosmic hard drive. It's not just a metaphor. The entropy of a black hole, the measure of its information content, scales with the area of its surface, not its volume. This is the holographic principle again. A lower dimensional boundary encoding a higher dimensional reality, like a simulation. In fact, the universe behaves in ways that strongly resemble a computational system with finite resources. There are limits to how much information can exist in a given region of space. There are maximums for how fast information can travel, what we call the speed of light. There are minimums for how small things can be measured, the Planck scale. These aren't arbitrary. They're constraints, programming limits. If space is emergent, if it's computed from entanglement and information flow, then everything we see is the result of deeper, invisible logic. Not a physical logic, but a digital one, a lattice of rules and relationships playing out in time, or beyond it. Some theories go further. They suggest that space and time themselves emerge from the structure of quantum information, that the geometry of the universe is a byproduct of entangled states. That distance is not physical, but informational. If this is true, then everything, every planet, every person, every thought, is a configuration of information, an arrangement of relationships, a node in a network so vast, so recursive, that its output is indistinguishable from what we call existence. Not simulated in the crude sense of pixels and processes, but rendered in accordance with perfect mathematical laws, executed, not imagined. And if information is never lost, then nothing is ever truly gone. Not the past, not the self, not the mystery. Only rearranged, only re-encoded. And perhaps, like all good programs, destined to be rerun again and again across the vast quiet loops of time. What if all of this, every strange pattern, every elegant constant, every burst of chaos laced with order, wasn't coincidence? What if it was evidence? Look back at the trail we've followed. Rivers and stock markets obeying Benford's law, chaotic systems drawn to strange attractors, quantum randomness that's perfectly predictable, simple rules birthing infinite complexity, a constant, 137, that seems written into the bones of the universe. Fractals in clouds and coastlines, turbulence with precise structure, avalanches and economies tuned to critical thresholds, black holes encoding information, photons computing their past from future observations. 10 patterns in chaos, 10 whispers from the code. Each of them, on their own, could be explained away. A quirk of statistics, a coincidence of math. But taken together, they tell a different story, one of startling consistency across systems that should be unrelated. Geology echoes biology. Physics mirrors finance. Neural networks share patterns with sand piles. These aren't just connections, they are repetitions. And repetition is the hallmark of design. Not design in the theological sense, but design in the computational one. A system optimized for emergence, governed by simple rules, rendered only when observed, encoded with constants that make life and complexity possible. A simulation? Perhaps. But maybe it's more than that. Maybe we live in a computational universe. Not a fake one, not a lie, but a deeply real one. One where the fundamental substrate isn't particles or waves, but logic, information, execution. A place where reality isn't a static thing, but an unfolding equation. And what does that mean for us? It means we are not just observers, we are participants. We are configurations of information, capable of reflecting on our own structure, capable of recognizing the echoes, capable of listening to the code beneath the chaos. It doesn't strip life of meaning, it enriches it. Because if all of this is calculated, if we are walking paths shaped by strange attractors built from bits that never vanish, guided by constants too perfect to ignore, then we are part of something vast, something elegant, something that may never fully reveal itself, but always invites us to look closer, to notice, to wonder, to trace the patterns, not because they prove anything, but because they point toward a truth deeper than certainty, toward a universe that may be running, not randomly, but beautifully. In every moment of disorder, there is design. In every quiet number, a voice. In every flicker of chaos, a hidden line of code. And in that realization, perhaps, we glimpse not the answer, but the right question. What else might be waiting to be rendered?